Welcome to Chapter 2. This is where thermodynamics really starts to get practical. Energy is everywhere. It powers our homes, moves our cars, and even fuels our bodies. But just knowing energy exists isn't enough. In engineering, we care about how energy moves, how it transforms, and how to analyze these changes systematically. This chapter gives you the essential building blocks. We'll break down what energy really means, how it moves in the form of heat and work, and how to write energy balance equations. Whether it's a simple cup of coffee cooling down or a massive power plant generating electricity, the same basic energy principles apply. By the end of this chapter, you'll have a solid understanding of how to track and account for energy in any system, a critical skill for any engineer. 1. Introduction. Let's start by understanding why energy is such a big deal in thermodynamics. Everything around us runs on energy, from your phone to factories to the entire planet's climate system. Energy isn't just about power generation. It's about how we live and how technology advances. But here's the catch. Different sources of energy have different effects on the environment, so how we convert and use energy really matters. Energy isn't just one thing. It comes in many forms. Think of thermal energy, like the heat in your coffee, mechanical energy, like the motion of a car, electrical energy that powers your devices, chemical energy stored in fuels, nuclear energy inside atoms, and even mass energy, as explained by Einstein. Whenever energy moves, it happens through heat, work, or mass flow, like heat in a boiling pot, work in lifting a weight, or fuel flowing into an engine. The rule book for all these changes is the First Law of Thermodynamics, which simply says energy cannot be created or destroyed, just transformed. And finally, efficiency decides how well we use this energy. A more efficient engine or process means less waste and more useful output, which is crucial in engineering and sustainability. 2 forms of energy. Let's break down what makes up the energy of a system. First, total energy is divided into 2 big categories. There's macroscopic energy, things you can easily see or feel, like the speed of a moving car or the height of a roller coaster. That's your kinetic and potential energy. Then there's microscopic energy, which happens inside materials, like how molecules vibrate or how atoms store energy. Kinetic energy is straightforward. It's the energy of motion. Anytime something moves, it has kinetic energy, calculated using the formula 1/2 mv². Potential energy comes from position, like when you lift a box up, it gains potential energy, and it's calculated using mgz. Internal energy is more hidden. It's what's happening at the molecular level. Sensible energy changes with temperature, like water getting warmer. Latent energy is involved during phase changes, like ice melting. Chemical energy comes from breaking or forming atomic bonds, and nuclear energy comes from changes inside atomic nuclei. In every process, total energy is a combination of all these forms, and understanding them helps you analyze any physical system clearly.
3. Energy transfer by heat. Now let's focus on heat. Heat is all about energy moving because of temperature differences, like when your coffee cools down because the air around it is colder. This is a key way energy moves around in systems. There are 3 main ways heat transfers. First, conduction happens through solids, like a metal spoon getting hot in a pot. Second, convection moves heat between surfaces and fluids. Think of boiling water, where hot water rises. Third, radiation moves energy through electromagnetic waves, like the warmth you feel from the sun. Sometimes we block heat transfer completely, which is called an adiabatic process. In these cases, no heat enters or leaves the system. We can also calculate how much heat is transferred using the simple formula Q equals mc delta T, where mass, specific heat, and temperature change tell us the heat involved. If Q is positive, energy is entering the system. If Q is negative, energy is leaving. It's a simple but powerful tool for analyzing thermal systems.
4. Energy transfer by work. Now, let's look at work. This is another way energy moves, but it's all about force and movement. Whenever a force acts over a distance, energy is transferred in the form of work. There are several types of work you'll encounter. Boundary work happens when gases expand or compress, like a piston moving. Shaft work comes from rotating machinery. Think of turbines or engines. Electrical work is from electric currents moving through a voltage difference, like your phone charging. Spring work involves elastic forces, like stretching or compressing a spring. We also have to keep track of direction with a sign convention. Positive work means the system is doing work, like when gas expands and pushes a piston. Negative work means work is done on the system, like when you compress a gas. This simple rule helps us keep energy accounting clear in thermodynamics.
Now we arrive at the most important law in thermodynamics, the first law, or the energy conservation principle. This law says something simple but powerful. Energy cannot be created or destroyed. It can only change forms. Whether it's heat, work, or stored energy, the total amount always balances. We express it mathematically as delta E equals Q minus W. This means the change in total energy equals heat added to the system minus the work done by the system. For closed systems, we use an energy balance where energy in minus energy out equals the change in energy inside the system. When we track energy transfer, we look at 3 ways it happens: heat transfer, Q, work transfer, W, and mass transfer, M. But remember, mass transfer is only considered in open systems where matter crosses the system boundary. This simple equation gives us a universal tool for analyzing engines, refrigerators, and any energy system you can imagine.
6. Energy conversion efficiencies. Let's talk about efficiency. This is where theory meets reality. The general idea of efficiency is simple. How much useful energy do you get compared to what you put in? The formula is just desired output divided by required input, multiplied by 100%. It helps you see how good a machine or process is at converting energy. Different devices have specific efficiency formulas. Pumps are about how well they turn mechanical energy into fluid motion. Turbines do the opposite. They convert fluid energy into shaft work. Generators turn mechanical shaft power into electricity, while motors turn electricity back into mechanical motion. In every case, we're looking for high efficiency because it means less waste and more useful energy. But no device is perfect. Some energy is always lost as heat, friction, or other forms. Efficiency helps engineers decide which design or machine performs better in practical applications.
7. Energy and the environment. Let's end by looking at why energy choices matter for the planet. Fossil fuels power much of our world, but they come with big environmental downsides. Burning them releases pollutants like CO2, NOx, SO2, and particulates, which cause air pollution. They also trigger chemical reactions that create smog at ground level. When sulfur and nitrogen oxides mix with rain, we get acid rain. The biggest long-term effect is the greenhouse effect. Gases like CO2, CH4, and NOx trap heat, leading to global warming. So what's the solution? Sustainable energy practices help. We can use energy more efficiently to get more output from less input. Even better, we can shift to clean, renewable sources like wind, solar, hydro, and geothermal energy. These options protect the environment while meeting our energy needs. Thermodynamics isn't just theory, it guides us toward a more sustainable future.